So our final speaker for this session is David Rosen, and he's going to be presenting a certifiably correct algorithm for synchronization over the special Euclidean group. And this is the first year that Wafer's doing a Best Paper Award as well, which we'll announce before the banquet.
Okay, sorry about that, guys. Okay, so yes, so I'm Dave Rosen, and today I'll be speaking about a certifiably correct algorithm for synchronization over the special Euclidean group. And this is joint work with Luca Carlona and John Leonard of MIT and Afonso Bandera of New York University. Okay, so the special Euclidean synchronization problem is the following. So you're given some collection of unknown elements from the special Euclidean group, so that is positions and orientations in d-dimensional Euclidean space, and you have access to some subset of noisy measurements between them, which we usually represent as elements or edges in some graphical network here. And what you would like is you would like to find an estimate for each of these individual poses that is most consistent with the set of available interposed measurements that you have. So this occurs all over the place in geometric reconstruction or estimation problems. For this audience, it's the formal model that's used in postgraph SLAM, but it also occurs in camera motion estimation, sensor network localization, and even areas as exotic as molecular structure estimation in chemistry and biology. And so there's a lot of practical applications that make this sort of an interesting and useful problem to be able to solve. Now the catch here is that this is actually a high-dimensional non-convex estimation problem due to the fact that the parameter space, the special Euclidean group itself, is a non-convex parameter space. And as a result, this problem is computationally hard to solve in general. So as we saw in some of the previous talks, the way that this computational hardness manifests itself in practice is through the existence of many, many suboptimal critical points for this maximum likelihood estimation that we'd like to solve. And unfortunately, these points in practice are not just suboptimal, but typically when you find bad local minima, they're so bad, at least in these problems, as to be effectively unusable. So as an example, here are just 3 randomly sampled suboptimal critical points from this problem whose correct solution is shown in the upper left here. And this actually was a real data set. This was captured in a parking garage in, I believe, the Stanford campus. And so to sort of see the practical effect of, or the practical danger in finding these bad local minima, I would invite you to try parking your autonomous car in this garage using one of these other maps. Okay, so this sort of raises the question then, so if we want to be able to solve this problem in practice, is it possible to actually develop a method that will enable us to reliably recover good solutions, at least under practical scenarios that we're interested in solving? And so in this work to address that question, what we do is we develop a convex relaxation of this problem with the nice property that this convex relaxation actually produces the exact globally optimal maximum likelihood estimate under reasonable levels of noise. And to solve that in practice, we also develop a specialized structure exploiting optimization method that allows us to recover these globally optimal solutions in a reasonable time frame with reasonable computational constraints. And so the payoff for this then is a method that we're calling SE-sync, and this is a certifiably correct algorithm for special Euclidean synchronization, meaning that this method is able to recover globally optimal solutions to a generally intractable problem for reasonable levels of noise. And not only can it recover these solutions, but it can actually provide a computational certificate that the solution that it has recovered is in fact the correct one. Okay, so because we're solving a maximum likelihood estimation problem, we need to come up with some sort of observation model that we're going to hypothesize for the noise that's corrupting our measurements. And so the one that we use in this talk is the following. So we assume additive Gaussian noise on the translational components of our relative pose estimates, which is typical for what you would see in the SLAM literature. However, we use sort of an unusual noise model for our rotations. We assume multiplicative rotational noise, which is sampled from a Langevin distribution. And for those of you who have not seen this before, the Langevin distribution is an exponential family distribution on the set of rotations. And intuitively, it plays a role for rotation-valued random variables that is analogous to that of the Gaussian distribution on Euclidean space. And so in particular, the way that you would actually sample a Langevin distributed rotation matrix is you would uniformly sample a rotation axis in 3 dimensions. And you would sample a corresponding rotation angle from a von Mises distribution, which for relatively high values of the concentration parameter is actually well approximated by a Gaussian. So intuitively, if you want a nice intuitive understanding of how this works, it kind of looks like a Gaussian over rotation angles. Okay, so in addition to providing, I think, a somewhat more natural model than sort of these exponentiated Gaussians for rotation matrix random noise, the real advantage of this is that because it's an exponential family distribution, it leads to a maximum likelihood estimation that's very nice. In particular, you'll notice that the objective down here is actually a convex quadratic objective in both the rotations and the translational states. Okay, so the advantage to this is that because we have this nice convex quadratic objective, if we think this will allow us to sort of further simplify this maximum likely estimation. So if you think for a moment about fixing the rotational estimates, just pick some, and consider now just estimation in the translational states, what you'll notice is that these translations, or this estimation problem in the translations, is an unconstrained convex quadratic linear least squares problem. And as a result, it's possible to then analytically solve for these translational states in terms of for a fixed value of the rotations using a generalized Schur complement. And so what you will get, after lots of tedious algebra, what you get is then a reduction of this maximum likelihood estimation problem to one that is in this simplified form. And without worrying too much about the details of what these intermediate matrices are here, you can see the paper if you'd like to get these in some more detail. The point here is that by virtue of having eliminated these translations, this maximum likelihood estimation now is just over the rotational states. So the nice thing about this is that this is a compact group, and so we've dramatically reduced the size of the search space that we have to consider. And these matrices here that appear in this quadratic form that parameterizes this objective each admit particularly nice interpretations in terms of the underlying graphical model. So there are things like graph Laplacians and things of that sort. I'm not going to go too much into the details here for this talk, but I'd invite you to take a look at the paper for the details on what those are. Okay, so now we have the simplified form of this maximum likelihood estimation, which is just over the rotations. And what we'd like to do is we'd like to develop a convex relaxation for this. So what this matrix R is you can think of it as being a row vector whose blocks are the rotational states that we'd like to estimate. And if you look at this estimation problem, you'll notice that this R only enters the objective in terms of this outer product. And so if you think about what that outer product looks like, well, it's going to be positive semi-definite because it's an outer product. And because each of these constituent blocks in R are rotation matrices, it's going to have a block diagonal that's comprised of identity matrices. And so if I think about what this means, what it means is that if I take every outer product, every pair like this that I could consider as a solution of this problem, I can embed each of these in this set C on the right-hand side here, which is composed, where I take the general set of positive semi-definite matrices, and I just consider the positive semi-definite matrices with block diagonals that are the identity. Okay, so why is this a useful thing to do? Well, it's a useful thing to do because the positive semi-definite matrices are a convex set, and this is a linear constraint. And so the intersection of these two sets is a general class of objects called spectrohedra. But the point here is that these things are convex because we have the intersection of a convex set and a linear subspace. And so what this means is I can think about expanding the feasible set of my estimation problem from these set of outer products of rotations to this larger spectrohedron. And the advantage to doing this is that this now gives me a convex relaxation because this objective, as we saw before, was also convex. Okay, and that's basically the main idea behind our approach. So the payoff here is that because I'm performing minimization on this side over a larger set, it immediately follows that the optimal value here is going to lower bound the optimal value of my original problem because I now have more options to pick from in terms of minimizing my function value. And if it so happens that the minimum that I determine for my semi-definite relaxation actually factors in this form, it admits a factorization of the sort that corresponds to my original problem, then it necessarily follows that whatever these factors are actually globally optimal solutions for the problem that I started with. Okay, okay, so that's fine as far as it goes, but you might say, well, why would I ever expect that to happen, given that I'm solving over this much larger space? Why would this ever occur? And in fact, actually, one of the main contributions from this paper is we actually prove that it does, at least when the noise that is on your sensors is not too large. So what this result basically says is that for a noise that's not too big, as measured by the deviation of this data matrix Q from its ground truth value, the semi-definite relaxation has a unique solution, so we can find this using any numerical optimization technique. And this unique solution admits a factorization of exactly the form that we are looking for, and as a result returns us a globally optimal solution to the original maximum likelihood estimation problem. Okay, so one of the things we'd be interested in then is characterizing sort of the actual performance of this method in terms of both computational speed and in terms of what is actually practically the regime of noise levels in which this method will succeed. And so in order to do that, we've conducted some simulation studies using these simulated grid worlds where we are sampling these things by varying the rotational and translational measurement precisions to see sort of what range of noise levels exactness holds for. And also the problem size to see sort of how this scales with computation. And we're going to compare this as a baseline to the Gauss-Newton technique using the so-called chordal initialization, which is basically the current state of the art. Pretty much all current state of the art techniques for post-graph SLAM are based upon some variation of this underlying optimization technique. Thanks. Okay, so what this plot is showing is it's showing the relative suboptimality bound of the estimates that are recovered by our method SE-Sync as a function of varying both the angular RMS error, the translational RMS error, and the size of the problems that we're considering. And so the message here is that pretty much in all the experiments that we've tried, we've noticed that this technique is essentially insensitive in terms of its exactness to the rotational level of noise, or excuse me, to the problem size and the translational noise levels. It does seem to have a dependence upon the rotational noise, which kind of makes sense because it's the rotations that make SLAM hard. So this is at least intuitively plausible. But what I would point out here is that this problem, the solutions that we recover, the exact solutions that we recover, or we recover exact solutions rather, for rotational noise that's up to somewhere in the range of 12 to 15 degrees. And if you think about what that corresponds to in terms of actual problem levels, I mean, 12 to 15 degree angular noise between frame alignment is quite a bit. It's about an order of magnitude greater than one would typically expect for laser vision-based systems that would be used in robotics or computer vision applications. And so somehow what this is telling you is that the range of noise levels over which this technique will succeed is not particularly restrictive. The other thing that's more surprising is that when you consider the computational cost of running these techniques, so here we're showing sort of the computation time as a function of these noise levels and problem sizes as well. The thing to note here is that this red curve is the Gauss-Newton technique, and each of these other curves here is various sort of slightly different flavors of implementation for the technique that I've just described. And the thing to note is the message of these techniques is that surprisingly, despite the fact that we're doing a global optimization, whereas Gauss-Newton is doing local search, by taking advantage of that simplified maximum likelihood form that I showed earlier, our technique is actually considerably faster than the Gauss-Newton technique, despite solving the problem globally. Okay, so just to show that this is not just restricted to these simple cube rules, we've also considered this on several large-scale SLAM benchmarks as well, and the behavior that we observed in the previous slide holds for these as well. So the message to take away from this is these are real-world examples. These are simulation results using off-target noise models. And the thing to note here is that in all of these cases, we recover globally optimal solutions, and we do so considerably faster than Gauss-Newton. In this case, between 3 and 15 times faster. Okay, so to summarize, we have a certifiably correct method. It recovers globally optimal solutions, and it's significantly faster than Gauss-Newton. Code's available. I encourage you to try it out. And the thing that I'm really excited about this is actually not just this technique, but what it implies about the possibility of producing certifiably correct techniques, not just for post-graph SLAM, but for a much broader range of techniques for things like binocular range-only measurements, so beyond just the post-graph model. Okay, so dirty laundry, real quick. The one thing we don't have yet is an analytic expression for this noise bound, but it doesn't seem to be particularly restrictive in practice. So with that, I would be happy to take your questions. Thanks.
I think in your work, you assume it's a Gaussian noise. Do you have any idea how to extend that to non-Gaussian, for example, multimodal situation?
Yes. So we assume Gaussian noise on going way back here. Okay, yeah. So we assume Gaussian noise on the Gaussian additive noise on the translational observations, which is I think pretty much the typical choice in post-graph SLAM. We assume Langevin noise on the rotations, but I think your question was really more about what happens if you have ambiguous data association. Was that right? Okay. So there's a couple of different ways that one could consider doing this. So one thing that one could try doing would be to say something like, okay, we can try to do an actual multi-hypothesis estimation, something along those lines, right? But I think what's more common, or at least I think the way that this usually arises in post-graph SLAM is, things like FabMap or place recognition techniques do a pretty good job of actually identifying the correct associations. The thing that we're really concerned about in those applications is the very small fraction of cases in which they get it wrong. And so one sort of intermediate approach between doing full-on multi-hypothesis estimation and single unimodal type stuff like what we're doing here would be to say the following. We'll consider the case in which we just have some bad measurements that we would like to identify and just filter. And that would be sufficient for addressing those problems, I think, in practice. The really nice thing about this is that I think it actually provides a path forward to doing, essentially this would be an outlier rejection formulation, if that answers your question. And the really nice thing I like about this technique is that what our sort of proposition here actually shows, I'm on the wrong slide. One way of interpreting sort of what this result actually says is that under sort of typical operating conditions, these two problems are actually entirely equivalent. So the usual nonlinear formulation of postgraph SLAM is actually entirely equivalent to a low-rank convex program with a convex compact feasible set and a linear observation model. And that's a very restricted class of geometries. And the nice thing about that is that there are already techniques that exist for being able to do very strong outlier filtering methods on that. And so I think this actual proposition might provide an alternative path forward to really designing robust outlier rejection techniques for that problem. Sorry, that's kind of a long-winded response, but I guess that was what I'm aiming at.
Maybe one more question? And your method is set to post-feature SLAM?
Post-feature SLAM. Yeah, so it should be able to do that as well, yeah, provided that you have what our method would require for that case would be that you have like range and bearing, where you have a total relative constraint between your features and your landmarks, or your poses rather.
All right, thank you.
Thanks.